Hello, and welcome to this presentation, Acoustic Modeling Approaches for Ear and Ear Canal Simulators using COMSOL Multiphysics. My name is Jensen. And first of all, I want to thank HBK and in particular Vince Ray for inviting me to present at their virtual conference here in September. Simulations, numerical models, digital twins, and virtual prototypes are being used intensively in the industry, in particular in the audio industry at nearly all stages of the product development. This also means that engineers want to simulate the standardized measurement setups. To do that, they need to be able to include the standardized test volumes such as ear canal simulators, couplers, etc. Today I'll give you a small introduction to various aspects of how these systems are simulated and can be simulated. This is how I look, well dressed at a physical conference a few years ago. Please get in touch with me. My email will pop up again at the end of the session. Otherwise, we'll have time for some questions also at the end. Also, a quick word about COMSOL, where I work. We are a simulation software company, and we have worldwide offices. I'm located in the Danish office where most of the acoustic development is going on. Headquarters for development is in Stockholm, and the business headquarters is in Boston. Our mission is to provide easy-to-use software solutions to engineering problems and to help our users get the most out of our products. We'll see some of these solutions today with regards to acoustics. Please visit our homepage if you want to see more details. Today I'll give you first an introduction to why you want to do simulations. I will then also try to introduce those of you who are not familiar with simulations to what they can do, give you a small example. I'll talk about microacoustics. Then I'll be talking about the BK Type 4157 ear simulator. You can see an image at the top right here. And I'll put that in context and show how you can either do full wave simulations or you can actually start to do hybrid finite element lump models, which can be useful in certain cases. I'll also talk about a full model, like you can see the image to the bottom right here, where the ear canal is simulated. You're not using any lumped models. I'll draw some conclusions and we'll have time for the questions. So why do you want to simulate? Well, and why do you want to use simulations? Digital prototypes, or actually high fidelity digital twins, they're called nowadays, are being used extensively in the development to more or less degree depending on the company and the industry. If you have a full digital twin, full virtual prototype of your product, you can start to take decisions at an earlier stage. So you can, what is called front-loading the development. So by having high quality simulation models of your products at an early stage, you can actually take decisions early and you can avoid problems in your development cycle. So you also take faster and better decisions for the management. They can decide on one options over another. Simulations are of course also good if you maybe in the old sense of using simulations, you could say is you can get an increased understanding and insight into the physics. You can look into a device and understand how an acoustic field, maybe you have some standing mode in your model. You can also use simulations for problem identification, troubleshooting. You can do optimization. And I think also a very important thing these days is to transform experience into knowledge. Why was my loudspeaker working when I did these things? Now you can look into it and understand why a solution actually worked. The image to the right is a nice marketing rendering of a microspeaker overlaid with the actual microspeaker cover. It's an Ole Wolf microspeaker, one of the examples we have in our tutorial library. So that's you could say a digital twin of that actual loudspeaker. Maybe some of you are not, that are listening in on the presentation, are not familiar with fine element simulations and digital twins and all these nice words that I said in the previous slide. So I've tried to come up with a small example to sort of give you an insight into what it is and what it can be used for. There are many applications we could discuss, but I've selected one with a hearing aid. You can see that in the sketch here. So this could, of course, also be an earbud, a smartphone, a loudspeaker, or any other device that uses sound, emits sound, where sound is handled. So in the sketch, this is just a sketch. So on the left, you have a hearing aid, you have a receiver or the micro transducer, the micro loudspeaker, and you have some tubing that goes out from the hearing aid and into the ear mold, and then there's an acoustic coupling between the ear mold and the ear canal. In order to develop your, in this case, hearing aid, you want to standardize a standardized setup to measure and test. So you need a standardized coupler volume, and this is what we'll be talking about today. So think of a very simplified version of the sketch you can see here on the image. It's a miniature loudspeaker suspended in a piece of ear mold tube, and it's attached to the ear canal simulator, the coupler volume. Here's the example of the very simplified or idealized example. So on the left is the actual measurement setup. So you have the small balanced armature transducer, you have the piece of ear mold tubing, and you have your coupler volume. You have a measurement microphone. And then on the image to the right, you can see the virtual model. You can see this model includes both acoustics, it includes vibrations, and it also includes the electrical and electromagnetic workings of the transducer. So this is a full multiphysics vibroelectroacoustic model. So you'll be able to, in your computer, simulate how this transducer will be vibrating, how it will be emitting sound, how it's coupled to various components in your model. It's not only beautiful visualizations, but you can also get, of course, all the measurements out that you would get with a standardized measurement setup. In this case, we're looking on the graph to the right. It's comparing the simulated vibration response with two sets of measurement curves of the setup, and the measurement curves are measured with a laser vibrometer. And we see an extremely good match here between the measurements and the measurement setup. The particular example is from one of our tutorial models that's called lump receiver with full vibroacoustic coupling, which you can find on our homepage or in our software. So with these virtual virtual models, you can perform all the measurements that you would do on a physical prototype, but you can do more, of course. You can look into them, look at the sound fields. And the good part is that you can actually test things before building them. So you can, maybe reduce the number of prototypes you need to build before you arrive at a good starting point. Prototyping, of course, will still be there, but the first prototype that you will build should be much better than if you had no insight at all. Here's yet another example from a so-called wax guard that is used in the ear hearing aids. So you place the small receivers, so you have a rendering of the little micro speaker on the left here, and this one is actually placed in the ear mold inside of the ear. And to protect the receiver, it's called the receiver in hearing aids on micro speaker, you have what is called a wax guard. So it's a small filter that protects from earwax, But that small filter, as you can see in the images to the right, also has some acoustic properties. In this case, it will introduce some losses in the model. The holes in this filter are extremely small. So in this case, in this example also, you can analyze maybe a subsystem, and you can, before sort of deciding how big the hole should be, etc., you can understand the acoustics. What are the implications when you add such a small mechanical filter, but it also has some acoustic implications. Good. In the applications and examples we looked at in the artificial ear simulator, the waveguide, all the structures or the perforates that were in this little filter, there are areas of what could be called microacoustics. So what is microacoustics? I think microacoustics, or my definition, is acoustics where the characteristic geometric length scales are comparable or smaller to, or smaller than, the thermal and viscous acoustic boundary layers. That's also what's called thermoviscous acoustics, or viscous or viscous thermal acoustics. And the losses in these boundary layers, which I will get back to in a moment, are the dominating dissipation mechanisms in the fluid domain. So to get the correct acoustic response, you need to understand those acoustic boundary layers. So let's look a bit at the physics that you need to include when you model these microsystems, and also when you model the ear simulators, because they certainly have, for example, very narrow slits. You get these losses. So here's an example. You have a wave propagating in a waveguide. The pressure with the colors, the propagating pressure wave, and with the points you see the particle velocity. So the air is moving back and forth, and a pressure wave is propagating. Now we zoom in on what happens at the wall. So in this case, this is a very wide duct, but now let's zoom in at what happens at the wall. Near the wall, you can see again the air is moving back and forth. On the surface of the wall, you have what is called a no-slip condition. So the air cannot move at the surface of the wall. And that actually introduces this transition from no air movement at the wall to the bulk air movement with the big dots. That's called the viscous boundary layer. And in that boundary layer, a lot of losses occur. A lot of viscous dissipation is occurring. So the thickness of this boundary layer is small. So it's, for example, 0.22 millimeters at 100 hertz. And it scales as 1 over the square root of the frequency. So it's decreasing with increasing frequency. So in devices where the geometric details are comparable to this boundary layer, that could be a pipe with a diameter of 1 millimeter, for example, then this boundary layer is actually dominating most of the waveguide. And it will introduce a lot of dissipation. So you need to include it. There's also an associated thermal boundary layer with this, but we will not look that much at this. So probably the most important effect of the boundary layer, the thermal boundary layer, is that it causes dissipation, as I've mentioned before. So that happens in narrow regions, channels, waveguides. The viscous boundary layer also changes the radiation impedance if you have a jump from a cross-section from a narrow tube to a large tube. And it's important, for example, as an example, in perforated plates, or in the image to the right here, when you have a mesh of some size. And the colors here are the magnitude of the particle movement. So you can see near the mesh itself, the air is not moving at all. So you get a lot of dissipation going on here. Another effect that is controlled by what is called the thermal boundary layer. So associated with the viscous boundary layer, there's also something called a thermal boundary layer. So small temperature fluctuations that happen in the fluid. And these introduce a transitional behavior from adiabatic to isothermal acoustics at very low frequencies. So that's an effect that is important inside of, for example, condenser microphones. can see an image to the right here where you have the magnitude of the temperature fluctuations. And at very low frequencies, you will move from normal adiabatic acoustics to isothermal acoustics. So effectively, the speed of sound is changed and the compressibility of the air, which is, you can see some of the numbers in the blue box to the left. But just to mention that this is why it's called thermoviscous acoustics or viscothermal acoustics, because you have both viscous and thermal effects in these processes. Good. Without going into too many more details today, I want to mention that in COMSOL Multiphysics, we have several ways to include the viscothermal loss phenomena. And the choice depends on the simplifications that can be made by the engineer. For example, if you want a quick answer with some lack of full details, or if you want to go in and do a full detailed analysis. So on this slide, I'm just sort of showing the various ways you can model these things. So at the left, we have what we call thermoviscous acoustics, which is we solve the full set of governing equations. It's valid in any geometry. So here we also solve for the movement of the small air particles. In the middle, we have something called narrow region acoustics, which is a simplified approach that can be used in waveguides of constant cross-section. It's also the approach used in classical lump models, where when you set up classical lump models for narrow waveguides. And then the last, on the right here, we have a feature called thermoviscous boundary layer impedance. So that's a way to include the losses in the boundary layers for larger models, where the boundary layers are not overlapping, so to speak. In that way, you can sort of collapse the losses in the boundary layers into a boundary condition. So various ways to tackle these important phenomena. Now let's look at the BK type 4157 ear simulator, or as it's also sometimes known, the 711 coupler. Let's look at some of the steps and considerations necessary to model the acoustic characteristics of the coupler. In the image here, we see a schematic cross-section. The color with colors, you see the air inside of the coupler. And here we see a pressure wave with high and low pressures as red and blue. At the top, you have the fixture end, I think it's called that. Here you can mount the system being tested, for example, using a DB2012 adapter to test earbuds. We're going to look a bit more at this later on. And at the bottom, it's where the measurement microphone is located. And again, I want to mention that the EK4157 coupler itself is a tutorial example you can find on our homepage, but also in our software. So when you model this with acoustics, you're not interested in the solid around it. In this case, you will only be looking at the air domain. So only the air domain is modeled in this case. On the left, I've sort of introduced or added the rest of the coupler just for visualization. In the slits, the very narrow slits that connect the main volume to the side volumes, you need thermoviscous acoustics to capture the losses correctly. The dimensions of the slits and the side volumes define the damping that allow the coupler to mimic the ear canal and eardrum system. So you have introduced, or these slits have been introduced in the design of this ear simulator in order to introduce some damping that is the same damping that is associated with the human ear. So that's why the coupler can be used as a standardized ear. So thermoviscous acoustics is used in these narrow slits here. In this particular model, the microphone is not modeled entirely, but it's added as an RCL impedance for the microphone. So the microphone is characterized by its damping, compliance, and mass. The model allows us to model the response of the coupler, and here are some of the results. So At the left, we see the transfer impedance, and the graph to the right, you see the microphone response. In red are the standard IEC curves, and in green, you see the response without the thermoviscous losses. So if you had just used regular pressure acoustics without including any losses, and you see clearly that the results are completely off. In blue, you see the simulated response where the losses are included. And you see that in the region where the standard is defined, you get very good agreement between the simulation and the standard. So this is all very nice. So now we know that we have full control, and we know we have nailed the simulation of the ear simulator. So you can start to extend the model with, for example, an adapter. As you can see in this example, if you look at the image to the right, an adapter has been placed on top. This is one of these adapters where you can place an earbud in it. So this is a DB2012 adapter. And in this particular model, you can see that I've made a sketch of an earbud at the top, so you can see what it looks like. But here only the rubber part of the earbud is modeled in green. Or actually it's not even modeled here, but I've just placed it here so you can see where it's sort of put into the adapter. In this particular model, at the top here where you can see the red, a lumped model or a SPICE model of the transducer inside of the earbud is coupled to the acoustic domain. We'll get back to this setup a bit later on. When you have the setup, you have your standardized coupler volume. You can start to test your virtual models of the earbud. So some company that models earbuds will be working on very detailed models of their earbuds, but they need to test these on the standardized volumes. And this is, of course, the focus today is not so much on how to model an earbud, but it's how to model the ear simulator and the adapters. And you could get, for example, a response curve out, as you can see in the image to the left here. This is a simulated curve of this particular setup. Good. So I want to get back to some of the modeling approaches that you can use, and I think they're quite important and something that engineers should think about. So I want to introduce you to a simulation approach that can simplify the setup and computational cost of the models. For example, if you use the same reference setup, you have the same coupler volume every time. And you're maybe not interested in what's going on inside of the coupler volume. Or maybe you have a few test setups that you're switching between. Then you can actually reduce those volumes and those parts of your simulation domain to be simplified with a lumped representation. And by lumped representation, I mean, for example, just an impedance condition, like we did for the microphone, but also transfer matrix, a transfer matrix that represents part of your simulation domain. Of course, this is applicable only when the plane wave assumption is fulfilled and your lump representations are valid. Let's look at an example. So this example, this is an example of a person that is doing a full multiphysics model of one of these small transducers. So this is one of these balanced armature transducers. So this is a very detailed model that includes electromagnetics, structures, etc., etc. So a very detailed, computationally expensive model. And then you want to test your transducer on your reference setup, as you can see in the top part of the image. So you have a long tube and you have a coupler volume. But these simulations are quite expensive, so you want to avoid modeling that volume every single time. So what you can do is you can reduce this volume to a transfer matrix, a two-port network. as you can see in the schematic at the bottom here. So you do a full fine element model of your transducer, and then you reduce the rest of the system to a transfer matrix representation. And we have dedicated tools to make this setup in COMSOL. Actually, both to compute a transfer matrix of a system if you want to simulate it, but also how to couple that transfer matrix setup to your fine element model. So that's easy to set up in COMSOL, and it has some advantages, as I've said. So when you have these hybrid fine element lump models, let's look at how you can compute the transfer matrix and how you then do the coupling afterwards. So here we have a particular test setup. So we have this piece of tube. You can see that on the image to the right, and we have the coupler volume. In this case, it's the 711 coupler, or the BK coupler here. So inside of COMSOL, we have some features that are called port conditions. So you can add a port condition at the inlet and a port condition at the outlet. And then what it will do numerically is that it will sort of apply a numerical two-load method, like you would do for measuring a transfer matrix of a real electroacoustic system. And then inside of the software, it will compute the transfer matrix of this system automatically. And you will get the transfer matrix elements out as data. And the nice part is that when you do this simulation, is that your transfer matrix information will include all the losses in the model. So, you know, the thermoviscous losses in the slits, the damping inside of the tube. Could be you had some perforations or anything like that. The transfer matrix that you use in your COMSOL model can also be imported, measured data, of course, or data that you have from some other source. It doesn't need to be simulated, but you can simulate it. And here's an example of the T21 part of the transfer matrix of this setup that I showed here. So you get the real and imaginary part of this part of the transfer matrix. The next step is to set up then the hybrid fine element lump model. For that purpose, we also have built-in functionality in terms of a dedicated boundary condition. We call that the lumped port boundary condition. This is, of course, a bit maybe obscure for those of you who have never used a simulation tool or COMSOL. But let's try and have a look at what you see here on the image. On the left, you see this detailed model of the balanced armature transducer that some engineer was working on. And then you click on the sprout and that boundary, and you apply this boundary condition, and then you get this nice settings window here to the right, where you can decide what kind of connection you want to add to that boundary. And in this case, it's a two-port representation, like you can see in the little sketch. You insert the transfer matrix elements, and then you want to terminate your two-port network with an impedance. And in this case, it's an impedance that is defined in terms of an RCL circuit. So the equivalent lumped model of the measurement microphone at the end of the coupler. We have a lot of functionality, so there are a lot of options here how you set this lump representation up. But it's easy. It's a click, and it's having the data ready, either measured data when you enter the two-port representation, or the model data, and then the impedance at the bottom here. Again, this can be an RCL circuit, but it can also be imported data, if you know an measured impedance curve of something. Let's get back now to the model of the earbud. So in that model, I mentioned briefly that at the top, there's actually a small transducer, but the transducer is not being modeled as a transducer, it's added as a boundary condition. And in this case, this lumped port condition that we just talked about on the previous slide is coupled to an electrical circuit, a SPICE netlist for this microtransducer, this balanced armature transducer. And inside of COMSOL, you can set up an electrical circuit and you can import a SpiceNet list. In this case, it's of a Knowles ED2346 balanced armature transducer. And that lump representation is then coupled to the finite element domain. So imagine above where I have my earbud sketch, there's actually a balanced armature transducer located, but it's modeled as a lumped representation. And many manufacturers have these lumped representations available. So you can get the SpiceNet list and import it into COMSOL, and then you can set up your model. At the bottom again, we have the RCL impedance for the microphone. So let me open COMSOL and we can just have a look at this particular example here. So this is the user interface of COMSOL. I will not go into all the details, but I will show you some of the things that we have talked about today already. So I have my coupler here with my adapter. And you can see in blue, it's the volume that is being modeled. So we are looking at the air inside of the coupler, of course. This is where we're solving for the acoustic equations. Then we have some of the boundary conditions that I've talked about today. We have at the top here a lumped port. And we have a connection time, which is of a type circuit. So it's connecting to an electrical circuit. And in this electrical circuit, we have imported a netlist of the balanced armature transducer. So it's a, electroacoustic lumped representation. And we have added this external I versus U node that couples this SpiceNet list here to my lumped port up here. So up here, the two representations, the lumped circuit and the finite element representation, are coupled together. And they're coupled in both ways. So it's a fully coupled model. Then if I go to my acoustic model again, I can click here and you will see that if you remember in one of my previous slides, I mentioned that in COMSOL we have several ways of including these thermoviscous losses. And in this case, I've included those with our narrow region acoustics feature. I zoom in and I've said, well, this is a slit. So I define that I say in this domain, I have a slit of a certain height. And then based on an analytical exact representation of a slit, the losses, acoustic losses of slits of this slit of this height is included in these domains. And I have a slit down here of a different height. So the losses are also included here. Yeah. In COMSOL, I will not go through all the details again. You then have a computational mesh. You run a study. In this case, I'm looking at some iso-standardized frequencies between 100 and 1200 hertz in 1/12 octaves. And then once I've solved the model, so this model runs really quickly, less than 2 minutes, you can then start to do your post-processing. So you can visualize the acoustic fields at various frequencies in your model. It's very nice for understanding maybe if you have a standing wave phenomena, you can look. Here I've made a mirror data set so you can sort of look at your model as if it was full. That's maybe something I forgot to mention. We're using a symmetry plane in this model. You can look at the flow of acoustic energy, looking at the intensity. You can look at sound pressure level again at various frequencies, and then you can do a lot of post-processing. In this case, I've looked at the microphone response. You could look at input impedance. You could look at pressures in points, etc., etc. So I could add one more plot here. It could be an octave band plot. And I want to start to probe what is going on inside of my coupler. Actually, what is the, maybe I had ideal measurement microphone that I wanted to locate here, just at the outlet of my earbud. Then you can plot that, and then you can overlay the results. Again, so the red curve is the sound pressure level at the ear, or the measurement microphone, that will represent the eardrum. And in this case, the green curve here that I just added, and make it a bit more visible here, that's my response just outside of the earbud. And in this way, you can compare different measurement points, but you could also compare various designs, various insertion depth of your earbud inside of the adapter, for example. Good. I just wanted to show you also a bit of how this looks inside of COMSOL. But again, I know for those of you who are maybe not familiar, this can be just me clicking around, but there are a lot of functionality for modeling these electroacoustic systems, and also for handling these microacoustic effects that are important, very important when modeling these systems of these scales. Good. Now, fully lumped or even the hybrid fem-lump models that we looked at are nice, but they're not always applicable. For example, you could have, maybe if you're into some very detailed modeling of your transducer, and you were looking at breakup or of some mechanical parts, modes in those mechanical parts, you could have non-plane phenomena at very high frequencies. If you are maybe interested in the ultrasonic response also of your system, could be you had porous media, could be you had a perforation. If you remember in the beginning, we looked at this wax guard. So if you had some structure which is not valid for modeling with a lump representation, then you go and you do your full model. And also with the lump models, remember just a word about those, you want to be able to predict the response. So you want to be able to predict the response of a system that you have not built yet. So you don't want to fit a lump model to measurements. Lump model can be made to fit if you have measurements, and you can tune the lump models. I think you want to use the lump models where you know they work and where they make sense, and you want to predict the behavior of your systems using full 3D fine element simulations. Just one example here where you can clearly see that you have a non-plane wave propagation. So this is again an earbud that could be inserted into an ear canal, and in this case I have a geometry of an actual ear canal. At the end of the right of the ear canal, there is the impedance of the eardrum has been added. So, and what you see inside here is the iso pressure contour lines, I think at 50 kilohertz. Here you see that inside of this ear canal, there are certain areas, whether the earbud sort of is in the ear canal, or when you have the bend in the ear canal where you have non-plane wave propagation. So in this case, you should be very cautious with using lump representation, and you will want maybe to model the full system. Good. So simulations and virtual prototypes are widely used in product development. Digital twins that I introduced in the beginning are now a tool that you use in your development. Also, more and more at a very early stage of your development, to be able to have a big impact on decisions further down development. Physics, we talked a bit about that. We talked about microacoustics in these microacoustic systems, your coupler volumes. We talked about thermal and viscous losses that are important to be included. We have there are several ways to include those losses inside of COMSOL, depending on the situation. Talking about microacoustics, you're probably looking at the animation to the right here, where we're looking at nonlinear microacoustic phenomena. So what happens if you have these grills, perforations in front of a small transducer? Here, the outlet of the microphone where you're playing at high sound pressure levels, you start to get nonlinear effects going on. So I just wanted to show you some even more advanced microacoustic applications that you should consider. These will introduce additional losses when you play at high amplitudes, and particularly what is important here is that you locally get very high particle velocities. So you get additional losses and also to some extent distortion. Good. We looked at the virtual test setups. So because you want to make digital twins, you also want to have a digital twin of your measurement setup. So you want a digital or virtual model of your standardized coupler volumes and standardized measurement setups. And then we looked at various modeling approaches where you can simplify certain setups by using hybrid finite element lump models. And here's engineering choices. Sometimes, you know, you are at an early development stage and maybe you don't want to include all the details. So you want to say, is solution A, B, or C the good solution? And then you can use a fast lumped representation or a hybrid lumped representation. And you can, of course, also do the full models to get all the full details. I think this made up the main part of my 45 minutes. Now it's time for some questions. Please don't hesitate to get in touch with me. I'll be happy to discuss any of these issues. Yeah, thank you very much for listening. I hope this was inspiring and gave you at least some ideas to what you can look at, or maybe ideas of how you can change or modify or simplify or add more details to your existing simulations. Thank you very much.